is by Didrik Lundberg from KTH, Stockholm, and it's on the mechanized semantics for data plane programming. On to you.
Yeah, thanks for the introduction. Nothing to add there. So first, let's set the stage with an introduction of the setting. Software-defined networking splits the functionality of a network element, such as a firewall or a switch, into a programmable data plane and a control plane. And the data plane implements the forwarding of packets, parsing the headers of incoming packets and using this to read entries from tables set by the control plane, which specifies certain actions to take, for example, setting next hop IP address. And the control plane is responsible for setting the content of these tables using these data plane logs as well as input from some admin or manager. Programming this data plane then is an ideal job for a domain-specific language. And this language is P4, which is the de facto standard language for programmable data planes. P4 compiles to a very wide range of different targets, like terabit bandwidth switches, such as the Intel Tofino, network interface controller cards, and even the Linux kernel. The hardware running P4 can be very specialized and heterogeneous and may use both ASICs and FPGA components. Performance is absolutely essential here. It's important to squeeze every bit of bandwidth from the hardware, which is reflected by the P4 language design. And when this hardware is increasingly put in places of critical importance, the need to model and verify the P4 language also increases. So what is this language P4 then? P4 programs consist of pipelines of programmable blocks. Parser blocks, which parse headers and work sort of like a finite state machine, and loop-free control blocks, which match against tables in the control plane. And P4 has no for loops or while loops, and the transitions in parser blocks may introduce loops, of course, but such loops are, in practice, always well-behaved and bounded by finite header sizes. And function recursion is also not allowed. There are no pointers and no dynamic memory allocation, and as such, no heap. The language allows specifying and reading from tables which map sets of values, like for example ranges, to function calls. And the entries of these tables may or may not be hard-coded by the P4 program. Extern functions and objects are central to the language, and they provide an interface to specialized hardware functionality, and their implementation is not written in P4. So both tables and externs may hold state between the processing of different packets and may be shared between parallel pipelines, the implication being here that they're interesting to consider for concurrency effects such as interference. Also, functions use a special calling convention where every parameter has a direction. So final values of out-directed parameters are copied out from the callee to the caller. And this enables something similar to call by reference in the absence of pointers and allows to control the side effects of functions such as these black box externs. And the characteristics of P4 in this list should then, of course, be used to inform semantics design. Let's look briefly at some example code. So the parser block shown here contains two states, start and parse IPv4. Every state ends with a transition to other states, and the start state selects the next state parse IPv4 or eject by matching the ether type field of the p.ethernet struct. Okay, so the body of a control block as shown here is the apply block at the bottom, and in this case the only table involved is IPv4 match, which is specified right above. So HOL4P4 is our model of this P4 language, and it is at its core a small step or structural operational semantics written in a heapless style, where every function has its own frame, each containing a store with values of all local variables and so on. And these frames are stored in a stack structure and only interact at the time of function call or return. We have also formalized the type system, whose notion of well-typedness guarantees progress and type preservation. And we've modeled some architectures, in particular the V1 model and eBPF architectures, with others like PSA and XSA under development, and the Intel Tofino model that we have not public yet. So our semantics model the entire pipeline from the input to the output of a packet. And all these things are formalized in HOL4. This doesn't mean that the work is all theoretical, of course, since we've also constructed an import tool to import real P4 programs into HOL4. So to be clear, what we mean with heapless style is that all variable names map directly to their values. In heap-based models, there's an intermediate layer of memory locations. But since P4 lacks pointers, this additional layer is largely unnecessary. And this heap can, of course, be cumbersome since you can't just disregard an unused part of it without a formal justification. And it might also need to be garbage collected. Now, aliasing is also possible in theory in heap-based memory, which can be a source of complications. So we use frames to ensure that the view of variables is always minimal. Let's go into more detail about the semantics. Semantics is split into 4 layers with the architecture layer on top, each defined only in terms of the layer below. The concurrency layer is a bit special, and I'll mention it separately later. So the reduction signature then of the architecture layer, the state contains list of incoming and outgoing packets, IO bar. The architectural state alpha, which holds extern data and variables passed between blocks. The block index I, which tells us which block we're currently reducing. Global variable maps in gamma G bar, and the stack of frames phi bar and the status T. So each frame then holds the body and local variables of a function that's currently being reduced. Calling a function, of course, pushes a frame onto this stack and returning pops one. And big E to the left there is the static environment containing all the immutable information about the P4 program and architecture. So from this big E, the frame layer semantics keeps big T with information about tables and big F with function signatures and bodies. And the main role of this frame layer is to use the statement semantics to reduce the top frame and handle copy out between frames. And in doing so, alpha may be modified since the extern objects can be updated, of course, block variables can be set, and status can be changed. So the statement layer semantics reduction has a similar signature to that of the frame layer, the difference being that there's only one single frame being reduced here. However, this reduction may result in a new frame, which we signify here by adding it above the reduction arrow, and this should make it maybe intuitively clear how this heapless formulation restricts the visible variables by construction. So finally, the expression layer semantics also needs the function signatures in big F as well as the variable maps gamma bar constructed from the frame we're currently reducing and gamma G bar. And note that expressions treat the variable maps as part of the static environment because they can't affect directly the values. And the phi here above the reduction arrow is the new frame that may result from a function call. Architecture layer semantics looks at the whole pipeline from a top level perspective, having only 7 rules for input and output of packets into and out of the hardware, initialization, regular execution, and finishing a programmable block. When block parameters are copied from alpha and back to alpha when initializing and finishing respectively. Transitions between parser states also handled by the architecture layer semantics and signaled by a special status. Finally, it governs functionality that the hardware may perform between the programmable blocks, called fixed function blocks. So the rule from the architecture layer semantics that handles regular execution inside a programmable block does so by using the frame layer semantics. And the frame layer semantics only has 2 rules. Both take the top element of the frame stack, takes the appropriate information from the static environment big E based on the function name associated with the frame, and then uses the statement level layer semantics to reduce the frame. So in the regular case, the status from the statement reduction does not signal return, and top frame is updated using the statement semantics with a potential addition of a new frame if a function was called. But if the status was set to return, then the frame return rule can be used. And this rule is responsible for performing the copy out behavior defined by P4's calling conventions. Note that copy out cannot be done at the statement level since the statement level semantics is unaware of the blocks below in the stack. Statement level semantics has rules for many standard language constructs such as if statement, return, and so on. So the transition statement is like a go-to for parser state, sort of, that you saw earlier. And extern and apply rules are also P4 specific. Let's take a look. In HOL4P4, calling an extern function or extern object method results in a new frame with a body that consists only of a single extern statement, here typeset with a black box viewed from the side. And the reduction of the extern statement is performed by first looking up the extern implementation ext in big F. And ext is then a function that updates the architectural state alpha and the local variable map according to the extern implementation. Can also read the global variables, and it can set the status t directly, which is used for return values. But note that this rule uses the heapless formulation to disallow extern functions to directly set variables in other frames, for example, which the semantics must ensure to follow the P4 language specification. For a heap-based semantics, on the other hand, one would have to be careful not to let this ext write to or even read from the entire heap, as this would make it too powerful. And note that this ext can be very complex. So the HOL4 extern implementation in the worst case may consist of hundreds of lines of code. Let's also take a look at table application. And this reduction simply takes the fully reduced key of the table, v1 to vn, and uses the static information stored in big T to obtain a function name, f prime, and some fully reduced arguments. And the reduction is then to a function call to this function f prime. The expression layer semantics similarly has many standard rules, arithmetic, logical operations, lots of bit fiddling. The select expression used to select next parser state that you saw. But the rule that's interesting here for semantics is the function call. So first, this rule uses the body and signature of the called function stored in the static environment. And then all arguments must be reduced according to direction. So in and non-directed arguments should be fully reduced to values, while out and in-out directed arguments should only be reduced to L values, like, for example, variables. And the new scope, gamma, is then constructed. So in-out directed parameters assume the value of the argument in the caller scope stack tupled with the argument as an L value. And out-directed parameters are initialized with indeterminate bits according to their type, also tupled with the argument as an L value. And recall, these L value arguments are stored so that we know what to copy out from the function, from the frame later when we're returning. And finally, the in and non-directed arguments are just copied in as is, tupled with bottom. The result of the reduction is the function value placeholder star f and the new frame consisting of the function name f, body s, and scope gamma. Okay, so we have also built a type system for our semantics, which is used to prove two nice properties of the semantics in HOL4. Type preservation simply states that if the initial state st is well typed, and if st is reduced to st prime in the environment E, then st prime is also well typed. The progress property states that if the initial value is well typed, then either there exists an st prime, such as st goes to st prime, or st is a final state. Then we did some other useful things. Now, having defined a set of semantic rules in an interactive theorem prover does not mean you automatically have a way of executing a program. Our semantic rules are relations between states that allow you to conclude whether the reduction from one to the other is valid. You can, of course, define a function that, given an initial state sigma, computes the state sigma prime resulting from one reduction. Effectively, this means just finding which rule to apply and computing the premises to obtain this sigma prime. And this we call an executable semantics, in the sense that you can directly use the standard evaluation mechanisms of the ITP to obtain this right-hand side given the left-hand side. And the semantics is deterministic, so this function only returns a single state to preempt questions. And our executable semantics has been proved sound, and the soundness proof states that every step of this executable semantics respects the relational semantics. Executable semantics passes all test cases that can be imported to HOL4P4 using the import tool when applied to a standard test suite of P4 programs with specifications for complete tests, a process which is totally automatic. To take a real P4 program and put this in HOL4P4, we've constructed an import tool. Use an external tool, Petra, to type check a P4 program and parse it into JSON, which is then parsed into HOL4 by our HOL4 JSON parser and finally transformed to the HOL4P4 format by this last stage, which does quite a bit of inlining and desugaring to properly represent programs. And as a proof of concept, we use the executable semantics to prove that the VSS example from the P4 language specification correctly decreases the time to live field of a packet by exploiting the capability of the ITP to evaluate the executable semantics with symbolic initial values and rewriting with assumptions. It was used in a paper to argue that it wasn't hard to construct a sort of complete symbolic executor for HOL4P4, something we made good on and proved to be true in a follow-up work which was actually presented last week. And this has already been successfully used to verify real P4 programs in industry, largest being somewhere just below 10,000 lines of code. So to show the usefulness of the small step approach, we have also extended semantics with a concurrency layer. And using this, we've shown that our model can accurately model interference between parallel pipelines with shared externs using an example from the concurrency model section of the P4 language specification. For future work, something like this could be used to model both the control plane and the data plane. So let's sum up this work, very briefly mention some other effort. Heapless semantics of P4 implemented in HOL4. With the type system with proof of progress and the type preservation, import tool can be used for real programs, and executable semantics that has been used for validation, and all of the code is open source and can be found in the HOL4P4 repo, also with an OOPSLA artifact available. Maybe to preempt some questions again, I would like to compare this very briefly to some other similar work recently published by others, but please check the paper for a more complete review. So several people have formalized P4 in the ITP COC. First, the COC formalization of the Petro semantics, originally written in OCaml for a POPL paper a few years ago. It's no separate publication for this COC version as far as I'm aware. And P4 Cub is an intermediate representation for making analysis tools made by a group at Cornell, including both a big step and a small step semantics. And there's also a group at Princeton that published the work at ITP last year, only working with control blocks in their publication at least, although I suspect there's more unpublished. So all of them in COC. I don't think they're proved sound with respect to one another. There's solid validation done for Petra at least. Main difference being the heapless approach that we use, and of course that we're focused on the small step semantics. Thank you. Any questions?
All right, thanks for the talk. Given that many questions have been preempted, we have time for maybe one or two.
Thank you. Good talk. I wonder if termination.
Okay, I'm going to guess.
Is termination is a problem for P4 programs?
So, right. So the parser, one could imagine in theory, an evil parser that maybe wouldn't even be possible to compile to real hardware. That would be really nasty to deal with. But for realistic programs, usually this is not that difficult. And with a small step approach, additionally, it's not so difficult to deal with.
So
the P4 specification is very vague in places.
Mm-hmm.
And different implementations make different choices about what to handle in those situations. How did you handle those kinds of, what was your sort of design methodology for handling those?
Let me see. So first I have to come up with some really vague thing in there. So I think one of the vaguest things that I encountered in the specification was how, so I mentioned this out directive.
Yeah.
Exactly. So when this is initially, right, you have these uninitialized values and how to treat them.
Yeah.
And actually for this work, they're just sort of a bit improperly modeled as a special type of, but really what I think is the proper way of doing this is that you have sort of a pseudo-random oracle, just as a sort of uninterpreted function in the model that then for concrete execution can be specialized to a specific pseudo-random function, but then, yeah, maybe I'm talking too much here.
All right, so let's send Didrik again.